and also contact angle measurement for wettability measurement. This is a centrifuge method that is used for capillary pressure, both for imbibition, drainage, and imbibition, and also with this system we are able to follow these curves by spontaneous imbibition and spontaneous drainage. We are also able to measure wettability of the rock system by USBM method. Another system that nowadays it is important to measure some parameters for each plug sample. For example, if we can able to measure capillary pressure and relative permeability together with instrument, this data is very important. But with this data, the name of this equipment is CAPRI, capillary pressure and resistivity index measurement. With this system, with 5 units, we are able to measure full capillary pressure curves during drainage, spontaneous imbibition, forced imbibition, spontaneous drainage, and secondary drainage. One of the most important questions in measuring capillary pressure during the centrifuge method is, what is the real time for equilibrium of capillary? But with this system, we are able to answer this question by measuring resistivity during each step. If the resistivity during each step established, we are certain that we reach the equilibrium in capillary pressure. For each plug, with this system, we are to measure different parameters. Capillary pressure curve during drainage imbibition, determination of wettability by combined USBM and Ammut method, and also resistivity measurement during drainage imbibition, and also with this system we are able to study hysteresis of saturation exponent during the changes of saturation. Also another equipment that we use in RIPI for relative permeability measurement, you see here, for unsteady state measurement, we calculate relative permeability from the data from this equipment by JBM method and Johnson-Buster-Newman method. This is another equipment for measuring relative permeability both for oil water, gas water, for whole core sample. Another method for measuring relative permeability is a steady state method. This system is for measuring relative permeability in a steady state measure. The difficulty of measuring relative permeability is in a steady state method, as you know, is monitoring of saturation during the core sample. With this X-ray system, we are able to measure saturation along the core sample during gas injection and water injection. And also with this system, we are able to measure three-phase relative permeability. Another technique for wettability measurement is Ammut method and also restoration the core sample. And also we need for each core sample to take CT scan images of the core sample. Without any damage of core sample, we are able to study the pore throat, pore size, and tomography of the core sample. That is very important for interpretation of data that we obtain in a special core study. This is an example of procedure of core analysis procedure. The first step, core gamma measurement and depth matching, core sampling, helium porosity grain density measurement, core cleaning and fluid saturation, core slabbing, standard gas permeability measurement, and also hydraulic unit delineation for sample selection for a special core study, sample selection for FRF for machinicity factor, pore size This special process, process for special core study, because we are not able to do all of tests with each plug sample. For example, if we use one plug sample for FRF, maybe some damage during the saturation and during the applying overburden pressure. We have to be very careful about the selection sample for special core study. Capillary pressure curves, formation resistance factor, pore volume, clinical permeability, and helium porosity measurement. And also relative permeability by water, gas, water, oil, gas, oil, X-ray relative permeability measurement, FRF and saturation exponent reservoir condition. It is the different, maybe for some reservoir it's changed, because for gas reservoir, oil reservoir, and maybe we have some difficulty during the production, we should be select a special test. But this is a special core study procedure. Another capability of RIPI for in upstream laboratory is PVT. In PVT study,
hello, excuse me, you have only 2 minutes.
2 minutes?
Yes.
I'm going to summarize our presentation because the name of my presentation was about routine special cores and PVTs.
Yeah.
Such as core study, we have all equipment related to conventional oil and gas fluid properties in RIPI, and also we have a special system. You see here the different generation of equipment in RIPI, from old to new generation of PVT system. This system is for wax and asphalting study by laser beam, determination the onset of asphalting and also amount of asphalting and wax. This curve shows us the power versus pressure laser beam during the PVT, during the pressure drop. You can obtain the onset pressure and also viscosity versus temperature. Measurement of viscosity versus temperature is used for wax appearance temperature. And also, here you see the different instrument of our laboratory, but in geoscience department, it is our activity related to EOR. By the equipment that we have in core study and PVT study, we are able to study each scenario related to EOR. For example, if we want to study the effect of special nano, special chemical to in an EOR process, we are able to do these tests in our laboratory: gas injection, miscible and immiscible, underground gases storage, polymer surfactant and alkaline surfactant polymer flooding. Here you see the different equipment that we have in RIPI for EOR study in lab. And another division of RIPI is another division of upstream of RIPI is geoscience. In geoscience, we have 3 main groups: petroleum geology, geophysics, and geochemistry. In petroleum geology, we are a lot of experience in sedimentological study, paleontological study, sequence stratigraphy, multi-well and multi-surface section correlation, preparation of conceptual model, and also another activities that are related to geology. You see here equipment. This system is for measuring, preparing the image, 3D image of the core sample. And if you want to orient the core sample, that we haven't any orientation of the core sample, this system is used to orient the core sample. And also another equipment to geoscience department we have. Finally, we have another department in RIPI for preparing a static model, dynamic model, and also finally master development plan that is necessary for EOR roadmap. Thanks for your attention.
Thank you, Dr. Kazemzadeh, for the very informative presentation. And now door is open for questions, comments. Dr. Salim, please. Yeah.
Which slide?
Yeah, the graph of
Oh, Shalom, yes.
reducing the
Yes.
risk and uncertainty. Yeah, that one. No, go back, please. Yeah, that one. What is your experience in Iran when it comes into translating research outputs to the field? You see, one of the problems is maybe the one you did put circles. What are the expertise? What do you do exactly to bridge that gap? Coming from research laboratory output and going into, let's say, a prototype, then application to the industry. What is your experience exactly? What do you do to bridge that gap?
One of the main role of RIPI, Research Institute for Technology of RIPI, is providing technology. For example, if we want to inject gas in the reservoir, one of the main phenomena is phosphate concentration in the reservoir. We have to study this phenomenon, the amount of phosphate and also the amount of phosphate. We have a lot of experience in this area. But also we prepare a lot of basic engineering data. For example, as you know, saturation exponent measurement is very, very difficult to measure in this laboratory. You are able to generate exact data in this area. One of our responsibilities. Another is gather all of this data, preparing FDP, field development plan. For example, preparing static model, dynamic model, and also master development. We did more than 15 game fields in Iran preparing NDP. And also, we started to go to the design pilot in this section. Design, testing laboratory, model, field, and process, design, field test, perform, pilot, monitor, and analysis. We did all of this. We have this job in RIPI. We are scanning. We have special software for this. Test laboratory. As we show you, we have a lot of experience. Model field and process. We are not in charge of model field. We give the data. We give or advice to the or client, and they are applying the field, but we check and we are involved during the job. But now we started to design a pilot in one of the animals. We did the job on it.
So to reduce your risk, you start with the pilot application rather than jumping into the mass scale, just testing it. You see, one of the problems of any academic institution when you have research output is getting that research output into the design and the prototype, then going to the industry. That's the most difficult part we are facing, at least here. And I wanted just to know what is Iranian experience in that. What do you do exactly?
To establish a spin-off company. The spin-off company helped us all of research to industry.
Dr. Salim, maybe I want to clarify one thing. RIPI, they do services more than research for oil companies in Iran.
Yes.
Okay, so it's more services than research. That's why
Yeah, because
they don't.
the graph in front of me is a complete value chain, which is very good.
Yeah.
Yeah, coming from testing, going into the expand to the field and development at the end.
Yes.
So this is a multidisciplinary approach. Reducing the risk is very good.
Exactly. Yeah.
You see the middle part of that one, where they start from design, the field test, up to the implementation.
Yeah.
That's the most difficult part of it. So I wanted to know how do they do it. That was my
Yes.
question. Thanks.
Yeah. Yes, Doctor.
Thank you, Professor. Actually, you showed like temperature and pressure up to 100, temperature 180 and pressure 10,000 psi. And this is if you compare it to the, let's say, the depth of a well, it is about like, you say 7 to 7.5 kilometers deep drilling. Do you have like wells deeper than this, and what research you do for that? Yes.
Yes, all of the equipment that I mentioned here, for example, CAFI system. This CAFI system works under 10,000 psi and also reservoir temperature. Some parameter is needed to measure under pressure and temperature.
Let's say higher than this, temperature and pressure. Do you do measurements on higher than 10,000 and let's say 200, 240? Because like if you go to 10 km deep, then you would... Okay, do you have like deeper wells than... how deep are the wells like that drilled in let's say, Iran? Let's say, how deep? Like... So you're talking about like 2 to 5 km? 2 to 5 kilometers, like deep. That's what you're talking about. Like you're not drilling deeper in Iran. That's what you say.
Yes, we have some reservoirs in Iran. For example, some in Iran is 6,000 meters.
6 kilometers. That's the maximum. This is why your temperature and pressure less than like 200. So, well, okay.
For example, in the depth of 6 kilometers, we have to apply overburden temperature maximum 700, 7,000 psi as a compounding pressure, and temperature maybe around 120 degrees centigrade. And it's possible to measure the parameter under the condition.
Okay. Thank you.
More questions? Yeah, I have one question. Do you have a tensiometer, IFT tensiometer, which measures IFT under reservoir pressure?
Yes, this IFT system is pendulum of method. The maximum pressure for the system is 10,000 psi. But applied pressure of the equipment is maximum 7,000 psi.
Okay.
And reservoir condition chill 150 degrees centigrade.
And the same for the viscosity. You have viscometer which can measure under high pressure.
Yes,
Okay.
you have high pressure, high temperature, viscometer, all in one.
Do you have in RIPI gas chromatography, GC?
GC?
Yeah,
Yes, we have.
because you didn't mention.
We have a special department in liquid for the downstream of liquid that we have a lot of GC for measuring components of gas.
Okay. Do you have steam injection rig?
We have
Steam injection rig?
simulate
Steam injection rig.
the steam injection.
Yeah.
We haven't any experience
You don't have in RIPI itself? You don't, okay. All right. Any more questions? Okay, thank you so much. Thank you, Doctor.
All right, so we can go. We'll take a half an hour break, coffee, and then we can join back at 11. Inshallah.
I think we should start the second session of this, and we would like to invite Professor Ayatollah Shahabi to the stage, please, to give his talk. Just to remind you again, we will remind you 5 minutes before the end of the lecture to be aware, so we are strict on timing. Thank you very much.
Yeah, I know that, especially when Saif is there. Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. So, because today I found out that too many people are interested into the nanotechnology, so I changed it suddenly, Dr. Yahya, if I'm allowed, okay, to nanotechnology-assisted thermal EOR, okay, instead of talking about the general thermal EOR. I'm sorry that it's a little bit, technical presentation. However, I hope that I can explain it in a way that most of the people can digest the essence of this presentation. Okay, so let's go ahead. Am I allowed, Doctor?
Yeah, sure.
Yeah, sure.
So let's see. Wow, what is that, sir?
That's not oil.
Is it the right presentation that I'm doing? Is it familiar, Doctor? Doctor Saif?
I think it is yours.
Oh, that's mine. This one is mine. Okay.
I think you're changing from EOR to biology.
Oh, yeah, that's right. Okay. So we'll talk about that later on. Anyways, okay, let's see what do we have here. As you can see in EOR, we are very interested really to move from the mega scale into the nano or micro scale. Okay, so this is the thing that I'm going to talk about it today, and then focus on the thermal EOR, how we can change some of the properties to enhance the thermal EOR process, okay? So if you look at the, the size of the reservoir that we're talking about hundreds of cubic kilometers, okay? So then it is, comprised of, very, very tight rocks in the order of micrometer, as you can see the size of the grain. And then when we go to the very small pores, and we talk about the layers, the films of the fluids that cover the pore spaces, we're talking about the nanometers. Okay, so why low oil recovery? Today we have several presentations regarding the enhanced oil recovery. So we want to know, why do we have the low oil recovery? We are talking about this issue mostly in the classes. Anyways, I'm not going to, to bother you too much, but however, it is very important to know about at least several of those, challenges that we are facing for low oil recovery. As you can see here, the pore scale heterogeneity is one of the most important parameters. In the rock itself, we have different pore sizes, okay? So the heterogeneity of the pore sizes is very important. The fluid interface heterogeneity is IFT, interfacial tension. So that's another heterogeneity that makes us another challenges for the oil recovery. Fluid-solid interface, as it's known, and as wettability is also very important. We also have other different heterogeneities in the reservoir, like the fluid heterogeneities. If we have different types of the fluids like oil, water, and gas, especially when we're talking about the liquids and gas, the properties are very, very different. So that makes up some difficulties for us to produce more oil. And also there are mega-scale molecules like asphaltene and waxes, okay? So regarding the pore scale, if you look at the size of the pore that you can see from a digital rock process, this process is well known today, okay, and the people are trying, as Dr. Kazem already explained it to us through the CT scanning. We can find it out what would be the shape and the size of those pores, and that's one of the, digital map of one of the rock, and you can see the different sizes and the heterogeneities that you have there. This is one of the main challenge for the oil recovery. Some of the oil will be trapped there. This is one more clear picture of the rock. There are pores, throats, and necks. Pores, throats, and necks there, and that's why some of the wetting in some cases and non-wetting phase in the other cases would be trapped in the pore scale, okay? That's the wettability. Everybody, at least those that they are familiar with the, with the oil industry, they know the wettability very well, okay? So regarding the wettability, what we are talking about a very thin layer of the fluid, of the coating that attached to the surface of the rock that would change the wettability of a rock from, let's say, water wet, natural water wet, to a synthetic oil wet rock, okay? So if you look at those pictures that they are SEM, actually they are ESEM because they are, they made it under the, environmental condition, and the fluid is there. For this case, as you can see, the fluid is completely covered the rock, the pore spaces, and here it is not completely covered the rock. So in this case, the wettability is different from that one. If we can change it, it affects the, the recovery, the oil recovery too much. So that's why one of the main reasons behind EOR, or the main mechanism behind the EOR process, is wettability changes. If we can change the wettability, so we may drop the residual oil saturation to a very low value in the specific type of the wettability index. Okay, I'm not going to talk about those issues that are very technical anyways. One of the other topic that we are facing is the interfacial tension, the tension that appears between the two immiscible phases. Those are the pictures from pendant drop, especially for the asphaltene precipitation, okay? Anyways, let's go further to find out what are the other challenges that we are facing. This graph is a well-known graph. We call it as the CDC curve, or capillary desaturation curve. Here you will see that we have the capillary number, the viscous force divided the capillary force, and here we have the residual saturation of the wetting and non-wetting. If you want to reduce the saturation of the wetting and non-wetting to a low value, we need to increase the capillary number. Increasing the capillary number means increasing the velocity, which is not possible in the reservoir. However, we can change the IFT and the wettability of the system to decrease the residual oil saturation. If we can decrease it to a very low value, we have achieved the goal, and we have produced the oil, bringing the money to the people of the country, okay? So that's the role that we are going to talk about. There are different processes for the EOR. You have known, you have read about them, or you know most of them: thermal, chemical, microbial. We not need to mention that one, because most of the people here, they are familiar with that process as well. However, we can see what would be the history of the EOR processes in the world, especially in the US. I would like to emphasize on this graph. I would like to, to let you know about the thermal processes. So this is very important for me to show you that the thermal, in most of those decades that we passed from let's say 1970 till now, was on the top of all of those processes. It's a very well-known one. It is well-known in Oman, and I will talk about that later on, okay? However, it depends mostly on the price of the oil. You will see as the price of the oil decreases, then the rate of the EOR processes decreases as well, okay? And as it goes up, then it goes up, but it is not exactly at the same time. We have a lagging time. In some cases, this lag may be from 5 to 15 years in some cases, okay? So I focus on thermal EOR because it was the topic of my, presentation. Okay, so this shows the mechanisms behind the thermal EOR. For thermal, whatever we do with the reservoir to increase the temperature, it appears in the, viscosity reduction, changing the viscosity from high value to low value, or thermal expansion, or steam distillation, or other, mechanisms. Okay. So we would like to increase the temperature of the reservoir. What do we face in the reservoir? We have rock over there. And the pores and the fluids are inside those pores, okay? So now we need to, to focus on the processes that we have around us in the Middle East. You will see out of, let's say, 9 different field experiences in the Middle East, 5 of them in Oman itself, and out of these 5, 3 of them at least, they are using the thermal process. So thermal is very important, not only for the heavy oil, but also for the light oil. We want to increase the, the rate of oil production. Therefore, we inject the steam, or we do in situ combustion to increase the oil production. So we will see that here we have Qarnalam, the first field. Actually, we started to working on that one with the help of Dr. Ali Al-Bimani and the group in 2004. We started that one. Then the Mukhayzana you will see, and the last one is the Amal field. Okay, so those are the thermal processes in Oman itself, and outside Oman we at least have 3 different pilots and field scale thermal processes around us. So it shows the importance of the thermal process, at least in the decade that we are studying the EOR processes around us. For the Oman itself, you will see Harwil as the miscible, Qarnalam thermal, Mukhayzana thermal, Marmul is the polymer flooding, and Amal also the the thermal. You will see how much oil is produced because of the EOR. The production before the EOR was the blue one, and after the EOR process is the the red one, well above the the previous cases of the without the EOR process. Okay, so that's the importance of this process. And then again for the Oman, I would like to emphasize on these 2 very big fields, Qarnalam and also the Mukhayzana. It is expected to produce more than 18%. Maybe now it is more than 20%. I do not have the statistics after 2010. This one was for 2010, and they expected something for 2012 to be increased to 300,000 barrel per day. I'm not sure if Dr. Yahya can help us in the statistics for that one. Maybe it is more than that one right now. Yes. Production from the thermal EOR. Yes, go ahead.
Little bit more.
Little bit more than 300. Okay, alhamdulillah. So that's a good thing that you will see. Almost one third of the oil production from the Omani oil reservoir is coming from the thermal process. So that would be important. So what do? They inject the steam from the top. This is for Qarnalam. They inject the steam from the top and then producing from the oil from the bottom, from those mechanisms that I do not want to take your time going to that one. So for the process itself, what happens? We do have wells for steam injection. Okay, so steam come into the behind the earth, inside the rock, maybe sometimes thousands meters down the earth, okay? And the steam goes into the rock, should penetrate into the rock, making the reservoir hotter, and then the process could help for more oil production, which we call them as thermal EOR. So what are the problems that we are facing at this stage? The steam should warm up the rock. So what is the problem here? See, when we have the hot fluid here, it should go through this barrier. What is this barrier? The barrier is the rock itself. But most of us know that the rock sometimes, plays like an insulator. The conductivity of the rock is very, very low, okay? You will see this schematic picture. It is real, okay? So you have a very hot, media here, but here you cannot feel it because of this rock. So if the rock itself is very low conductive, so how we can push the steam into that one and produce more oil by conduction technique, okay? I have a table here to show you the thermal conductivities of different materials. Let's say for the copper, that it is a high conductive material, it's almost 400, aluminum 200, okay? But for the, that's for the mostly the hydrocarbons, very, very low value. For the sand, also very low value. And for the sandstone, the reservoir that we are talking about is 1.7 or something like 2 compared to 400 and 200. So if we increase it, it means that we can increase the, the amount of heat that it could penetrate into the reservoir, increasing the efficiency of the steam injection. So that's the reason behind this slide, okay? So we are talking about very small pores, thin layer of the, of the coating that could be placed on the surface of the rock to change the property of the rock. Usually we do that one for wettability alteration, but now we have a technique to increase the conductivity, the thermal conductivity of the rock by nanotechnology. This belongs to almost, let's say, 400 years ago, almost 400 years ago. In the scale of, let's say, millimeter or centimeter, okay? But now we're talking about nanometer, okay? This was the, the process that we even worked here. Professor Yahya, Dr. Yahya, know this guy, Zargari Saeed. He was here for a long time, staying with Henna and working on the microbial enhanced oil recovery. And we got this picture out of AFM. Those are the bees. Here are the microbes, okay?